So let's move over to theory of vibration considering the MDOF system, or the multi-degree of freedom system. So at first, the example here may appear to be a single degree of freedom system, since it's only composed of a rigid bar attached to spring support at the ends. But since the response or the coordinate at each end, as defined by the spring stiffness K1 and K2, are independent with each other, so the system can now be tagged as a multi-degree of freedom system, or specifically a 2-degree of freedom system. So to come up with a solution of MDOF system, we need to simply take again the free body diagram of the rigid bar, or the rigid beam in this case, which is attached to the spring. And for simplicity reason, we neglect first the damping, the damping force on the system. So if we will look on the FBD of such system, taking note this reference line, which is the original position of the bar, okay, we can come up with forces that constitute the spring force and the inertia brought about by the mass, which is concentrated at the center of gravity of this bar element. So the inertia force brought about by the mass is actually composed of the translational and the rotational uh, part, which I already explained to you on the SDOF solution. And assuming that your rotational inertia is given by the letter J here, so the I alpha that I normally place on the previous lecture is now uh, made into a different variable, J theta double prime, or double dot, okay, where I and J are simply equal, and alpha and theta double dot are simply accelerations. These are of course rotational or angular accelerations. So consider now the reference as your x1 and theta. So your choice of reference is dependent on how you want the uh, particular variable to be solved. So in this case, we want x1 and theta to be the primary variable. We can now uh, derive this equation by simply taking note of the free body diagram, that summation of forces vertical is simply 0, and summation moment at the first support is also 0. By the way, theta here, of course, is defined somewhere here, referred to the horizontal line. So this is now your angle theta. So correspondingly, your acceleration will be theta double dot. Okay. So for the first summation, so we have k1 x1 added to mx double dot added to K2 X2 will simply constitute your summation of forces vertical, and summation of moment at 1 will only constitute these two forces rotating at this support, and your J theta, uh, which is also counterclockwise in this direction. That's why you will notice that these are all positive values. And substituting now a value for x, okay? So this x here is actually the position which is not known to us because this is at a point in between, okay, the primary coordinates x1 and x2. So we can simply substitute this variable into uh, the theta variable and the x1 variable here, okay? So your total displacement at this point now will be simply x1 plus a certain eccentricity defined multiplied by theta. So what is that eccentricity? So the eccentricity is simply the location of the center of gravity of your bar element reckoned from the one of the spring supports, okay? You can refer it to any point, but of course for simplicity of moment summation, we refer it to one support so that one um, force here will be cancelled, no? Okay, so this uh, value of x now here, okay, will simply be x1, okay, so whatever is this displacement at the left plus an additional displacement that is given by the value x theta, uh, this angle here, okay, which is assumed as one of the primary coordinates, theta. Okay, since this is an acceleration variable, so we simply add double derivative in each and every variables concerned, noting that E is a constant here. Okay, and so is true with your summation of moment 1. We simply substitute your x2 here. By the way, x2 here can also be substituted in terms of this primary variable x1 L theta, and so is true with the summation moment definition or equation. Okay, where your coordinate, which is normally in terms of translational coordinate, is now converted into a a coordinate which is the initial, okay, displacement of the left support, and the theta coordinate, which is also the rotational displacement referred, okay, or based on this left support here. So this is now our coordinate of reference that you consider. Of course, this simplification can readily be undertaken, and if we simplify, okay, if we simplify this equation here, we can come up with this equation and eventually lead to, okay, to this equation here. Okay, so simplifying now, uh, these two equations can now be transformed into a matrix form. By the way, uh, this first equation is actually a simplification of this one here. Okay, and there's a J here. This is the summation moment simplification there. Okay, so you might be confused where did this came from and where this came from. Okay, so but we have to take note that for a bigger degree of freedom or larger degree of freedom system, we need to translate it into a matrix format, so that your equation now will be in this uh, systematic array vector formulation. Okay, so simply a matrix formulation. So if I want to expand this, I will arrive with this same equation. Okay, and just take note that your your matrix here on the mass, you call this now your mass matrix, and your stiffness matrix are not, okay, at all symmetric, and this gives us some difficulty, especially when the number of degrees of freedom is very high. So choosing a coordinate is actually the key to having a simpler, okay, simpler matrix form that will ease up the computation. And if we choose x and theta as our coordinate system instead, okay, instead, so this is x and theta instead of x1 and theta. Okay, so we now choose x and theta as your coordinate. This is the one that we will be arriving at. Okay, this is not simpler than the other one, but take note of the following. Okay, so the mass matrix in this choice of coordinate is actually diagonal, and you call this a dynamically uncoupled matrix. Okay, so uncoupled because your off diagonal elements are actually zero there, unlike what we have in this. Okay, this is much more difficult to process later. So the stiffness matrix may not be diagonal, but of course we can come up with some more simplifications later to make it appear easier to process. And we call this system now a statically coupled system. So when you look at the word uncoupled and coupled, um, the perhaps the main thing you have to understand here is the complexity of processing the uncoupled system is higher, no? But it's not. It is still doable, okay? But if the off-diagonal terms in the stiffness matrix, these off-diagonal terms become 0 or are 0, then the system is completely uncoupled. And we have actually converted the two matrix into, or sorry, the two equations, which is an equivalent equation of this matrix, into two independent equations. And by a proper choice of the coordinate system, the MDOF system may be totally uncoupled, which is simply converting into an independent SDOF system. Okay, so it might be lengthy because you have n independent system, but the method of solving the equations will now be more simpler than uh, an uncoupled, okay, matrix as defined by this equation, okay, and this equation. Okay, so if we consider now a shear building model, a 2DOF system, this is a 2DOF system. They are equivalent. No, these are all equivalent system. The stick, okay, model, the the mass damper stiffness model, okay, or the mass spring dashpot system. They call it sometimes a mass spring dashpot or a damper system. Okay, so we will arrive now with same matrix, okay, formulation using the principle that I stated above into an uncoupled, okay, mass matrix and a coupled stiffness matrix. Okay, but if you will take a look at these equations now, this lamp mass system, always the mass matrix is uncoupled. Okay, so it can be a force undamp or a force damp vibration, but in this case there are no given damping coefficient or damping ratio, so we have to settle for this force undamp vibration. So in all cases, your mass, your C and K matrices are now symmetric. Okay, so they are now symmetric. So look at this, and this is dynamically uncoupled, statically coupled, but they are symmetric, and that's what makes the better choice or the best choice of coordinate system to uh, consider if you want to have a simpler solution. Okay, so that ends the first part. I will continue discussing on the second part uh, the process of determining the natural frequencies in the MDOF system.